So what are you guys?
We're the Smartwood family!
Hey guys, so the point of this video is kind of twofold. So in the first part of the video, what I want to do is go back to an old roundtable problem. So when I did that problem way back when, it was to show sort of like different counting techniques, okay? And while that's good, I had a question or request. Actually, it's probably not best to do the video now because I'm congested, but a student had a question, so I wanted to respond as quickly as possible. Was there a faster way to do that problem? And in fact, there is. There's a much faster way, but I'm going to do it painfully slowly, not in the actual technique, but sort of in how we explain it. Because if you apply this sort of thinking to other problems, it could work out really well, but if some of these assumptions are off, it could go really badly, okay? So I want to do that. And then the second part is I want to work on a harder roundtable problem, okay? And we'll get into that in a second. But first, let's do the one I did before, which is basically you have 10 people, and those 10 people are seated around the round table, like that. And let's say, for the sake of convenience, that we'll fix in a sec, you can tell, all the chairs apart. Like the chairs are labeled, chair 1 up to chair 10, okay? And the question is, if you seat these 10 people around this round table, right, and you pick out two specific people, say person A and person B, what is the probability that person A and person B sit together, okay? So what's the likelihood that happens, okay? And I did it in that video, so if you want to reference it, I'll try to, put a little note up here so you can link that video to see that way of doing it. But the request was to do this more quickly, but I want the assumptions, right, to be absolutely clear. So imagine you have any seating, okay? So you're gonna take the people and you're gonna seat them around this round table, okay? Somewhere you have to place person A. So let's say we put person A right here, okay? So you place person A there, okay? Let's make this concrete, okay? So let's say person A is sitting in chair 1. This won't matter in a second, but let's start with it. So now you have all these arrangements that have person A sitting in chair 1. Okay, what about person B? Where could person B be? Well, person B could be in any one of the 9 remaining seats. Okay, so I want to think of 9 total possibilities where person B could be. Okay, now how many of them give you what you want, where A and B are together? It seems really mellow, right? It seems like there's a spot here and a spot there. So there are really 2 choices. B could be here or there. And it seems like maybe the answer is 2 out of 9. This is actually the correct answer. Okay, and it can be this quick, but you want to be careful and you want to make sure that all the assumptions kind of fit in place. So I'm going to break this down slowly. So what's happening is if we put person A right here, okay, then we think, okay, if I were to place person B here, I'm going to count this as one arrangement. Okay, so I think of, let's call this like arrangement alpha. Okay, there's a reason why I'm doing this. We have person B seated to the right of person A. Okay, but then think, what about everyone else? So once we place B there, does everybody agree you can seat the other people any which way you want? There are 8 chairs remaining, and you can arrange the people in the 8 chairs any way you want, and that's going to be 8 factorial. The key thing here is, in this alpha setup, what's happened is that you place person B to the right of person A, right? So let me start using some color here. Maybe something like this. Okay, we place person B right there. Okay, no big deal. And do you agree? For everyone else, you have 8 possible seats where you can place them. So actually, when I think of setup alpha, I'm actually thinking of a whole cluster of possibilities, right? Where you place A in seat 1, B to the right of him, and then everyone else, there are all these different ways. In fact, there are 8 people left to seat in 8 chairs. So if you reference the old video, there are actually 8 factorial ways of placing the remaining people, okay? But now, I wanna look at what I call case B, or beta, let's say beta, sorry. Case beta is where we put person B to the left of person A. Okay, so let's look at case beta. Okay. So in case beta, how many different possibilities are there? Well, when you place A, let's mark this, let's erase this. When you place A down in seat 1 and B to the left of A, then you still have 8 people, right? The same 8 people, and you can put them in any one of the remaining 8 seats. So again, if you think it out, that's gonna be 8 factorial different ways. The 8 factorial part's really not that important. What's important to understand is this case alpha and this case beta, right? You've got the same number of possible arrangements for the remaining 8 people. Like there's 8 factorial ways of arranging the remaining people in setup alpha, but there's also 8 factorial ways of arranging the remaining people in setup beta. Does that make sense? That's absolutely key, because sometimes it's really easy to do harder problems where you're thinking about this and you're like, oh, okay, well, I could go there, and we're done. But those setups are not equal, because if it had been in the case that, in setup alpha, where we place B to the right of A, if there were 8 factorial different ways of seating the remaining people, but in setup beta, where you place B to the left of A, if it had been in case there were like 7 factorial for some reason, right? And you didn't have equal numbers, then this way of thinking does not work, okay? So Now we think about this. What do we have so far? We have two good setups, right? So I'm going to draw this. We have setup alpha and setup beta, which have equal numbers as our two good setups. We're going to add up the number of arrangements that exist there, okay? But now we're going to look at the total number of setups, right? What are the total number? Well, A goes in seat 1. We have that. Okay, so A goes in seat 1, okay? So now let's look at this again. So A ends up going in seat 1. Now let's think about B. So in general, how many places can you place B? Well, B can now go into any of the 9 remaining spots, right? So there are 9 setups here with B, ... 9 of them, okay? And here's the key step. Once I place A and I place B somewhere, right? In each of these setups I've drawn with these boxes, right? How many ways are there to arrange the remaining people? Well, it's going to be 8 factorial because you still have 8 seats left and 8 factorial ways of arranging those people. Okay? So the key to seeing this is that we have 2 guys up here, 1 and 2, right? Where once we place the first 2 guys, there are 8 factorial ways to arrange the rest, right? But on bottom, we have 9 different ways of placing the first 2 guys. But once we've done that, we have 8 factorial ways of arranging the rest. So what we really have here is 2 boxes up top and 9 boxes on bottom. Right, so this is 9, this is 2. And the key is each one of these boxes, if I looked inside and saw how many arrangements are there inside of these, they're all the same, right? So the number of arrangements in here is the same as this, is the same as this, is the same as that. If that weren't the case, we couldn't do this slick trick. And in harder problems, I know this might sound obvious, in harder problems, difficulties arise because there's a subtlety where you think these boxes all have the same number, but in some cases they don't, okay? So anyway, I know that seemed kind of long for that, but when you're comfortable with this, running this in practice, this is a very quick solution. You place A down, how many total choices for where B goes? 9. Okay, of those 9, how many give you what you want, where B is next to A? 2. So the probability really is 2 out of 9, where this is the number of ways of getting what you want over the total number. Now, I mentioned in the beginning of this video that when you do this arrangement, right, I said that you could tell the chairs apart. I also made a side comment, I don't know if anyone noticed it, but basically saying something like, it doesn't actually matter where you could tell the chairs apart or not. And the reason why is this. Technically, the way we solved this problem was assuming you couldn't tell the chairs apart. Because if you can't tell the chairs apart, you can place A anywhere you want. And then all that matters once you place it is where everyone sits relative to A. So the solution that we ran, technically, where I computed 2 out over 9, that works if you can just place A somewhere, and every chair that you place A in is equivalent because you can't tell the chairs apart. So what matters is where everyone else sits relative to A. However, theoretically, if you're looking at labeling the chairs, like chair 1, chair 2, chair 3, all the way up to chair 10, right? Then you get different arrangements. So do you remember how we had the 2 possibilities up top? Where A is sort of seated next to B, right? Well, actually you have to take all of those and multiply by 10 because we assumed that A was in chair 1. But you have all these arrangements with the same number of possibilities where A is in 2, 3, 4, all the way to 10. However, when you look at the total possibilities, where we had, say, this is 2, 9, right? Each one of those assumed that A was in chair 1, but A could be in any one of the chairs again with equal likelihood, right? So you multiply by 10. And you can see that these actually cancel because that factor of 10, because they could be in chair 1, 2, up to 10, that happens both up top and down below. It happens in all the good cases you're looking at and also with all the cases, period, okay? So again, I might be belaboring this. You might be thinking like, why is he doing this? I would kind of do it that way anyway, just instinctively. That's fine, but in harder problems where it becomes more subtle, and if people want me to, I can find problems that are like that. It's not so obvious this is going on, okay? All right. Anyway, all right, so let's try it again. Let's try a round 2. So what's going on in round 2? Round 2, we're gonna do the round table problem, a harder version.